In the last video, we posed the big question of frequentist inference. How can we simulate all the ways that a dataset might have turned out but didn't? In this video, we'll look at one answer called parametric resampling. The idea is very simple. The first thing we need is a probability model for the data. Of course we do. There's no way you can do any useful machine learning or inference at all without a probability model. We've looked at this climate dataset in earlier videos, and we came up with a probability model. Our model proposed that the temperature is a sinusoidal function of time, plus a secular trend, plus Gaussian noise. This is just one possible model for this dataset, of course, not some absolute truth. Once we've stated a model like this, it's easy to see how to simulate the multiverse. Before simulating, we're going to decide on a readout function. In this case, the readout we were after was estimated rate of temperature increase. In other words, we want to read out the maximum likelihood estimate for one of the parameters of our model. Next, we fit the model, i.e. we find maximum likelihood estimates for all its parameters. And then, to generate a new synthetic dataset, we just sample from the probability model that we just fitted. Nothing could be simpler. Finally, we want to report the spread of our readout function. We can just simulate many synthetic datasets, evaluate the readout function on each of them, and plot a histogram. One thing I want to stress. Our readout function t has to be a function of the observed data, something you can compute given the data. It's not allowed to depend on the unknown parameters. This is a common mistake I see in exam answers. You're asked to measure the uncertainty in one of the parameter estimates, you're rushed for time, and you don't notice that your readout function depends on one of the other unknown parameters. A readout function like this, something you can compute given the data in front of you, is called a statistic. Next, what do the outputs look like? Step 3 suggests you plot a histogram. Here's the histogram I got for possible values of the rate of temperature increase. Once you've got a histogram, you could stop there, or what's common is to report a confidence interval. You could report a two-sided 95% confidence interval, for example, and say, here are two bounds, an upper and a lower, and I'm 95% certain that the estimated rate of temperature increase falls between these two bounds. There's a one-liner in NumPy for getting these bounds, numpy.quantile. But there's nothing magic about choosing bounds with equal-sized tails, as I've done here. I could perfectly well ask for a one-sided confidence interval and say, I'm 95% certain that the estimated rate of temperature increase is less than this upper bound. It's up to you which confidence interval to report based on what your audience wants to know. Okay, let's work through some examples. We're given a dataset, and we believe that the values are drawn from normal of mu comma sigma squared, where both parameters are unknown. Find a 95% confidence interval for mu hat, the maximum likelihood estimator for mu. We better start by working out what the maximum likelihood estimates are. The answers should be familiar to you from the very first part of the course. Next, we just go through the 3 steps. It's exactly the same 3 steps every time. Step 1, define the readout statistic. The question tells us we want a confidence interval for mu hat, so I'll define a function that takes in a dataset and computes the MLE mu hat for that dataset. Step 2, define a function for generating a random synthetic dataset from the fitted model. So all I need to do is compute sigma hat and then generate a synthetic dataset just like the original using my fitted parameters mu hat and sigma hat. Step 3, sample the readout statistic by generating lots of synthetic datasets and computing the readout statistic on each of them. In my code snippets, I'm writing the list of sampled values with an underscore, and I'm putting it in bold to emphasize that this is a list. Here I'm also showing the two-sided 95% confidence interval. Okay, all done. Now for another example. Where this whole procedure gets interesting is where you turn an interesting question about your dataset into a question about a model parameter. Here's an example. We're given two datasets, x and y, and we want to know how similar they are. We're asked to model the x dataset as drawn from normal of mu, sigma squared, and the y dataset as drawn from normal of nu sigma squared. We can estimate the difference between the two datasets using the statistic nu hat minus mu hat. Actually, I said something misleading. I said we're given two datasets, x and y. What I should have said is we're given a dataset consisting of some x values and some y values. When we do maximum likelihood estimation, we should always write it out in full as the likelihood of all the data given all the parameters. Here, all the data means all the x's and all the y's, and all the parameters means all three of them, mu, nu, and sigma. I won't go through the process of fitting this because you've seen so many model fits already. Let's just look at the code. It's exactly the same three steps as before. First, define the readout statistic on line 5. This just implements the readout statistic that the question asked us to evaluate. Next, define a synthetic dataset generator, lines 10 to 12. Finally, sample the readout statistic and plot a histogram if you like, and find a 95% confidence interval as the question asks us to do. The only thing that's worth dwelling on here is the synthetic dataset. As always, when I say dataset, I mean all the data that we're given. Here we're given two collections of readings, x and y, and so when we generate a synthetic dataset, we have to generate two collections of readings. The next example is a bit political. Here's a question about fires in the Amazon. In summer 2019, the news was full of stories about Bolsonaro and how under his watch the number of fires had dramatically increased. Here's a plot of the number of fires each year. The dataset contains day-by-day numbers for every year, but I'm only plotting the cumulative counts for each year up to the 29th of August to match the news article, which came out on 30th of August. And indeed, the 2019 figure is very high. It's more than twice as high as the preceding year. The question only asks about 2019 compared to values since 2011. That's from reading the subtext behind this news article here. 2011 is when the previous president, Dilma Rousseff, came to power, and the news article is implying a policy difference between her and Bolsonaro. So let's go ahead and answer this question with the confidence interval. First, we need a probability model for the data. When you're a data scientist, no one tells you the right probability model. You have to figure it out for yourself. And in fact, there's no such thing as the right model. All models are wrong, but some are useful. So let me offer not one, but two models. The first model is exactly what we used in the previous example for looking at the difference between two groups. That's where you typically get probability models from. You build up a large repertoire of models by reading about the models that other people have proposed, and then you either copy them, or better yet, you take away from them the nifty features of their models so that you can mix and match them yourself. The question here asks us about the difference between 2019 and the years 2011 to 2018. So I definitely need a model that's got enough parameters to express the idea that 2019 is different. And I think there's a subtext in the question that says there's nothing much to distinguish the individual years between 2011 and 2018, so I'm not going to do so in my model. Of course, you're totally free to propose a different model. Now, look at model 2 on the right. This one's a bit different. This model says that values from 2011 to 2018 are sampled from normal of mu sigma squared, the same as the left-hand model, but then it's got a different equation for year 2019. It suggests normal of mu plus delta sigma squared, and then asks us to find a 95% confidence interval for delta hat. Actually, these two models are exactly the same if you look at them in the right way. To see that, first of all, they are both linear models. Here I'm writing them in the way we wrote linear models earlier in the course. I'm using bold symbols for vectors. The feature spaces for these two models are identical. The specific features they use are different, but in each case the features span the same feature space, so the models express the same thing, just with different parameterization. So it actually doesn't matter which of the two models we use. We've already seen the code for fitting model 1, so just for the sake of difference, I'm going to fit model 2. And also I'm going to write out the code a bit more elegantly by thinking about what we're doing as a linear model. First, we need to know how to fit the model. I've written out formulae for mu hat and delta hat here, but you could perfectly well get them using sklearn.linear regression. Also, I've written out the maximum likelihood for sigma. The formula here is generic and it applies to any linear model. We derived this formula for sigma hat earlier in the course. Next, we go through exactly the same 3 steps as before. The only thing that's slightly interesting about this code is the way I'm generating the synthetic data set. I'm doing it linear modeling style. I first fit the linear model, and that gives me predicted values for each of the years, and then I use these predicted values to generate the new synthetic data set. In the end, the 95% confidence interval turns out to contain 0. I am not confident that 2019 is different to 2011 through 2018. It's borderline, but not quite enough evidence to be confident. It is asking a lot to look for evidence of a policy change from just a single number. There's nothing intrinsically wrong with that, it's just it'd need a pretty extreme single number. If we had more years, we'd get a clearer picture. It would be good to rerun this analysis using 2020 data. Okay, so that's how we find confidence intervals for statistics. There are 2 things I want to note. First, there's nothing sacrosanct about the way we're reporting uncertainty. Here, we're measuring our uncertainty by means of a confidence interval. In the next video, we'll look at hypothesis testing, which is an alternative to confidence intervals. Second, there's nothing sacrosanct about the way that we're generating synthetic data sets. Any method for simulating the multiverse is a leap of faith. It has to be. How could we possibly deduce what might have happened when all we know is what did actually happen? In the following video, we'll be looking at a different way to simulate the multiverse.